Welcome to EDU World Space.
Now this curve, this function that is y is equal to e to the x halves plus e to the minus x halves, which if we draw in the xy plane, the x and the y axis.
Here's a clean and professionally formatted presentation of the
there,
calculation shown in the
it's
image.
a curve something like this.
Application of the work energy theorem, WET. From the work energy theorem, the force F is given by
So
F
we
equals
want to
frac
consider,
text KE, where KE equals
happens if we
kinetic
have,
energy, S equals stopping distance.
points
If I'm given
A
for object A, FA equals
B,
frac 100,000,
and we
0.10.
rotate this region
For object
about the
B,
x
FB equals frac
axis.
225,
So if we rotate
1500
about
equals
the x, we're gonna
0.15
obtain
text space n. And
a
force
shape
ratio frac FA,
that
FB
looks like
equal frac 0.10,
this,
0.15 equal frac
like
2 null result. A box frac FA,
some
FB.
sort of
Would you like a PDF version of this
curve
explanation?
cone like that. So we will have this region. So we want to compute what is the area. What is the area? Which in the end we would like to see that is equal to the volume enclosed by this area. So we call this area D, the volume enclosed by D, that region D. So the way to compute this area is the following. So you have this, we can call this f of x. So this area would be area is equal to 2 pi times the integral from a up to b of f of x times this part is ds, that would be 1 plus f prime squared dx. So for this function, all f prime is going to be equal to, so you have derivative of that would be e to the x halves, but by the inner derivative we get a half. And then for this one we have also e to the minus x halves, but by the inner derivative we get a minus a half. So that this object here, this square root of 1 plus f prime is going to be equal to square root of 1 plus f prime squared would be equal to the square root of 1 plus this square, which would be e to the x halves, minus, we can subtract, we have common denominator, minus e to the minus x halves, and well, that square divided by the 2 square, so that this is equal to square root of 1 plus, well, this square is going to be this term square, which is e to the x squared, x halves squared is e to the x. And the middle term is the mixed term is 2 times the product of these two, which is 1, so minus 2, and then plus that square plus e to the minus x, and then all of that divided by 4, so that if we add these two guys, we have the square root of 4 plus e to the x minus 2 plus e to the minus x, and all of that divided by 4, so that we can simplify that to the all this 4 and that minus 2, those two cancel, and then we have this term e to the x plus 2, adding 4 minus 2 plus e to the minus x, and well, square root of 4 is 2, so we have that, and then so the area would be equal to area, it's going to be equal to 2 pi times the integral from 0 from a to b of our function, that is e to the x halves plus e to the minus x halves, that is our function. Now there, and then that times this square root of e to the x plus 2 plus e to the minus x, and then that divided by 2 dx. So one thing that we can do is we can cancel these couple of 2's, and well, we can note that inside we have this term can be seen as the square of that is equal to this. If we square that, we're going to obtain this term square, which is e to the x, the middle term 2 times, so the middle term is this times that, which is 1, 2 times, so it is that, and then this term square is e to the minus x, so that with the square root, well, it will cancel because the term is positive, so this area is going to be equal to pi times the integral from a up to b of e to the x squared plus e to the minus x squared, but also all that term then from the square root, because since we have the square root of a square is the term itself, so it would be that term x e to the x halves plus e to the minus x halves dx, and then we can see that this term is the same, so this term is equal to e to the x halves plus e to the minus x halves squared. So well, if we rotate this area and we consider what would be the volume of that region, so we can A and B, so we have some curve like this. I'm assuming that our A and B are the same. If we rotate that region, we'll have something like this, the shape the same as above. But if we were now to consider what is the volume of this region, so we would need to add each of the slices here, each of the transversal cuts here of these slices, and one slice of this for a particular x here would have area pi times all the radius squared, but the radius is precisely this. The radius is our function, so it would be pi times our function squared, which is the same integral that we have here. We have here pi times integral from a up to b of f of x squared dx, which is, well, to compute the volume, we would need just to add all of those. Pi f. So these two are equal, and the reason why those two are equal is because for that particular function we have that integral is equal to this integral that was the original integral to compute the surface area. like this. So for this function, it happens that these two integrals are the same for any values of a and b, which was, well, this is the surface area about rotation, the surface area about rotation of x, and then is equal to the volume of, well, also rotating the graph about x. So it is because of this, for that particular function, for f of x equals to e to the x halves plus c to the minus x halves.